with a long surname. Okay, so as everyone knows, concurrent programs are difficult to get right, especially when non-conventional synchronization mechanisms and locking schemes are used. Now, the fact that modern microprocessors employ weak memory models makes things even harder. So it would be nice to have a way to verify our programs against our specifications or find bugs. Now, one technique that addresses this issue is bounded model checking. So bounded model checking verifies a program, a concurrent program for bounded length executions. It's a technique that is easy to use. It's completely automated. It's effective. In most cases, it's proven to be effective since it's based on the observation that most bugs have shallow causes. It's technically straightforward. It has been implemented in a lot of tools, and it has seen some use in the industry. But the thing with bounded model checking is that it doesn't scale, and it doesn't scale both in terms of time and memory. So one technique that addresses the memory issue, the memory aspect of the state explosion problem, is stateless model checking. Now, stateless model checking is simply based on the observation that given a concurrent program, one can explore the state space by just exploring all threaded interleavings, but without actually explicitly storing the visited states. And since, of course, this can lead to repetition, there are other techniques like dynamic partial order reduction that avoid redundant exploration. And what these techniques do is that they just explore some representative traces from some equivalence classes. And in these settings, there are some algorithms that are optimal, but all these techniques are for sequential consistency. So stateless model checking has been extended to handle weak memory models, for example, by modeling the stored buffers of the weak memory model or whatever. But the thing is that this process gets more complicated, and there are more interleavings to explore, and stateless model checking for weak memory gets slower as the memory model gets weaker. So in this table, you can see some results for NITHAG. NITHAG is a stateless model checking tool that's considered to be a state-of-the-art, and it supports both sequential consistency and TSO. And of course, NITHAG gets slower as the memory model gets weaker. Now, this doesn't need to be the case. So I'll present our approach, which we have implemented in a tool called RCMC, which manages to outperform the state-of-the-art stateless model checker, even though it operates under a weak memory model. So our contribution is a novel technique for verifying C++ concurrent programs under relaxed memory. And we do that by just enumerating all execution graphs of a program instead of enumerating interleavings, like the dynamic partial order reduction techniques. And we also avoid, by construction, the generation of any graphs that are inconsistent. We also avoid generating the same graph twice. And we also do that without recording the graphs that we've already generated. So in the paper, you can find the proofs, but our technique is both sound and precise, and is also optimal in the absence of read, modify, write instructions and SC accesses. So the first two bullets above, the fact that we avoid generating inconsistent graphs and the fact that we avoid generating the same graph twice only apply when there aren't any RMWs and SC accesses. So our tool and approach target the RC11 memory model, which is just a repaired version of the C11 memory model fixed to avoid some out-of-thin-air behaviors. And we've run a variety of benchmarks, and we have shown that our tool outperforms the state-of-the-art model checkers. So the key idea behind our approach is that instead of enumerating interleavings, which are just total orders on the events of a given concurrent program, we enumerate graphs, execution graphs, which are partial orders. And we use an axiomatic approach to do that. So for example, for this simple program here, one trace of this program could be this, where, okay, X is initially 0, and there are 3 threads. The first thread is executed first, then the second, then the third. We can suppose that all accesses are release acquired or whatever, or relaxed. This particular trace can be represented by this graph. So the WX0 is the initializer write. This is just a write that gives the initial value to the memory location X, which is 0. And then there are other events. This is the event of the first thread, of the second, and of the third. These events are connected by various relations, like reads from. So, for example, this arrow here means that the read reads 1. So we perform some sort of graph-based model checking, where our goal is, given a concurrent program P, we want to enumerate all consistent executions of this program P, but without generating the same graph twice and without generating any inconsistent graphs. So I'll start by presenting a simple example of our approach. This is not the way we actually do it. It's a naive approach, but it helps understand the technique. So suppose that we have this simple program. X is initially 0. The first thread writes to X, the second reads, and the third again writes. So we keep a set V, which contains all the execution graphs that we've already visited. Initially, this set V contains only one graph. It's the one that has only one event for now, and it's just the initializer event or events. These are the events that give the initial value to all the memory locations used in the program, and then at each point, we pick any graph from the set V, we pick an event that hasn't been already added to the graph, and we just add this event to the graph. So we pick the only graph available, we pick, let's say, the write of the first thread, and we add it to the graph. So now we have this graph, and we repeat the same procedure. So in this naive approach, again, we pick the only graph available, we pick an event that hasn't been added to the graph, and we add it to the graph. So here we are about to add a read, and this read can read either 1 or 0. It's consistent to read both these values. So, of course, we need to explore both of these scenarios, and we'll end up having 2 graphs. So in the first graph on the left, the read actually reads 0, and in the second graph, the read reads 1. Again, we repeat this procedure. We pick a graph from the set V, we pick an event that isn't already in the graph, and we add this event. Now here we're about to add a write. So before we're adding, in general, when we are adding a read, we're not certain that all of the writes that are present in the program are also present in the graph. So in that sense, when we're adding a write, we may need to revisit some of the reads that are already present in the graph. It's like a read reading a future value, a value that isn't present yet. So what we do is when we actually add a write, we revisit some of the reads that are already present. So in this case, we can revisit this read, since it's consistent for this read to read 2, and we'll end up with 2 more graphs. In the first graph, the read is not revisited. It continues to read 0. And in the second graph, the read is actually revisited, and it reads 2. And we continue with the same procedure, but the first 2 graphs are done. So there's no more event to add in these graphs. And then we take the only graph available, and we're about to add a write. So we check if there are any reads to be revisited, and in general, we can revisit this read. But the thing is that if we actually try to revisit this read, we'll end up with this execution twice. So what we do is, before actually, in this naive approach, before actually adding a graph in the set V, we need to check if this particular graph prefix is already present in the set. So that's why we need to keep this set V. And in this case, we do not add the graph where the read is revisited because this graph prefix is already present. So we add 1 more graph, and this graph is also complete. And one interesting observation here is that the order in which the events are added to a graph is relevant. So that's good, but it's not the best we can do, because all these graphs are actually stored in memory, and we do not want that. So we modify our goal, and instead of just enumerating all consistent executions without generating the same graph multiple times, without generating any inconsistent graphs, we had one more goal. The goal is that we don't actually want to record the set of the graphs that we've already generated. So the question here is, how do we do that? We do that by not just keeping execution graphs, but not just dealing with execution graphs, but with dealing with a slightly more sophisticated data structure, which contains both the graph and these revisit sets. So these revisit sets are just some sets of reads for each graph that indicate which of the graphs read can be revisited when we actually extend this graph. So here on the bottom is an illustration of these revisit sets. So you can imagine that this read that is green is actually revisitable. So if we add another write at some point later, this read in the middle can actually be revisited and be forced to read from the right we're about to add, but the read on the left is not revisitable, which means that it will never be revisited again and that this read from edge is final. So we slightly changed the model checking procedure, and when we add a read, we make this read revisitable in only one of the sub-explorations that will arise. With this approach, we only examine one graph at a time. And when we're adding a write, we select which subsets of the reads that are in the revisit set can be revisited. We revisit those, and in the sub-explorations that these reads are actually revisited, these reads are removed from the revisit set. So let's see the same example using this stateless approach. Again, we start with the initial graph. We add the first event, which is a write. There's nothing to revisit. We're fine at this point. And then we're about to add the read. Again, this read has two options. We'll examine both of them, not at the same time. This can be done either recursively or by using a stack. For the purpose of the presentation, I'll just suppose that we that we explore these executions recursively. But we need to explore both of these scenarios. In the first scenario, the read reads 1, and it's not revisitable. And in the second, it reads 0, and it is revisitable. But we'll deal with them only one at a time. So suppose we continue with the first option. Then, again, we're about to add a write, but when we add a write, the read is no longer revisitable, so it's not revisited, and we get this graph, which is complete. And then we continue with the alternative option for the read. So now, when we're about to add the write, this read is actually revisitable. So again, we need to consider both of these scenarios. In the first case, the read is not revisited, so we get this graph, which is complete. And in the second case, the read is actually revisited, and it is also removed from the revisit set. The execution is complete, but even if there was another write, in this particular sub-execution, this read wouldn't be revisitable. This is another example. We have a program with 3 threads. The first 2 threads read from X, and the third thread writes to X. Suppose that we've already added the events of the first 2 threads into the graph. So we have this graph, and these reads are all revisitable because there is no alternative option for them to read from. And then we're about to add a write. So in general, 6 more executions will arise. So one point is that, for example, in the execution where the read to A is revisited, which is this execution on the bottom. So in this execution, this read will be revisited to read 1, where it was reading a 0 on the execution on the top. So in this execution, this read is removed from the revisit set. But the interesting thing is that its suffix, this read to B, is removed completely from the graph. And we do this because when we actually change a value that a read reads, this may affect the control flow or thread local execution. So we need to remove the suffix of read that is revisited from a graph. And another point is that when we, for example, revisit the read to B, which is this case on the bottom left. Not only we remove this read from the revisit set, but we also remove all its prefix from the revisit set. Because if the read to A was to stay revisitable, then another write could come along, revisit this, remove the suffix, and in general, we could get repetition. So these are some experiments with only reads and writes. You can find more experiments and benchmarks in the paper. In these benchmarks names, the numbers are next to the name are actually the number of threads in this particular benchmark. Our tool is RCMC, and we compared against NeedHug on SC, TSO, PSO, and Power. And we also compared against CDS Checker. CDS Checker is probably the tool that's closer to ours, since it also operates for the C11 memory model. Our tool is implemented on top of the LLVM infrastructure, so in general, it can handle most C and C++ programs. And as you can see in these benchmarks, we outperform the other tools in most cases, except for some trivial ones. So more things that you can find in the paper is how we handle consistency. So when we're adding a read or a write, it's not consistent to read from, for example, when we're adding a read, it's not consistent to read from any write. And when we are revisiting some reads, we cannot revisit every possible subset of reads that there is. So there are some constraints that we need to address. You can also find out how we're handling RMWs and SC accesses, and why we're not optimal under C and RMWs. Our algorithm has two modes. It can operate either under the RC11 memory model or a weaker version of the RC11 memory model, which can be faster and more effective if there aren't any concurrent writes, because in weak RC11 we avoid recording the modification order. And you can also find more benchmarks and details about the implementation. So in conclusion, I presented an approach for stateless model checking, the RC11 memory model that's both sound and precise. It is also optimal if there aren't any RMWs and SC atomics, but works very well in practice even if there are RMWs and SC atomics. But the key point that I'd like to make is that model checking for weak memory model doesn't need to be harder than model checking for sequential consistency. And in fact, our approach works very well for the RC11 memory model and the relaxed access and release acquired accesses, but doesn't work so well for SC because it's harder to express this, the constraints that are needed for SC consistency in terms of program order and RF and whatever. And as future work, we could try to generalize and apply this approach for other memory models, and also try to come up with an optimal approach for RMWs and SC. Thank you.
Okay, we have ample time for questions. Is there someone in the room who wants to answer a question in person? Move to the microphone, please. I'll ask the first highly voted online question meanwhile. So how do you handle loops? The graphs are infinite or, well, infinite.
Sorry, what was the question?
It's the question about handling of the loops, because
the loops in the programs, or
the loops in the programs.
In general, in the
I'm assuming the person who asked the question can correct this.
The programs that we verify have to be finite and deterministic, so you can't have like infinite loops. They are unrolled, the infinite loops. The loops in the graph, there aren't. I mean, these graphs are partial orders in PO and RF.
Okay, if the person who asked the question didn't get answered, they can post a follow-up. Please, go ahead.
So in the traditional DPOR kind of algorithm, the only thing that is stored is the current execution trace. So it's one trace.
Sorry?
Now you're storing some graphs. So I assume that the memory consumption will be higher than in the past. And things, the programs that you were showing on the slides are small in terms of like experimental evaluation. Have you looked at the memory consumption, like as you have like larger programs, and how fast is the memory consumption going up?
So the question was how do we handle the memory consumption and whether we have tested larger programs?
Yeah,
okay.
Yes.
This slide may be slightly misleading, but we don't actually have more than one graph stored in memory, and these graphs are just some, these are very simple and do not consume as memory. So in effect, we have only one graph at a time in memory, and there are some arrows and edges between the events, which are just pairs of locations. I mean, each event has a thread and its position within the thread, and then we have relations between the events, but this doesn't consume much memory. And we can use like a stack to store all the alternative exploration options and just keep one graph in memory at a time. And if we have tried verifying larger programs, the first benchmarks that I demonstrated in the beginning, the last one, the QSpinlock, is like extracted from the kernel. It's like 1,500 lines of code, and our tool scales very well in both in terms of time and memory.
I'm going to ask one online question and then we move to you. So the question is, how are your graphs different from the ones that are done in the HERD tool? If you know what that tool is. HERD, H-E-R-D.
These graphs are similar in the sense that they depict a particular execution of a program, but HERD actually uses a naive approach, and all these graphs are stored, and it doesn't scale well. We've shown an axiomatic approach, like an operational presentation of an axiomatic approach. Let's say that we only keep one graph at a time in memory, but it's the same way of depicting the execution of a program.
Okay, please go ahead.
Yes, I have a question about this benchmark. It seems that you're comparing doing model checking on the axiomatic semantics against model checking on the operational semantics. Is it possible that using your technique to verify the SC programs which use an axiomatic semantics, then it would be able to boost up the benchmark for model checking those programs?
So the question was whether we would be able to use this axiomatic approach where?
For SC programs, basically. Well, I mean, if you use that, I believe you can use that for SC programs, right?
Yeah. This technique is sound for SC programs. It's just that it is not optimal. So we actually use this axiomatic approach to verify SC programs.
Okay. And so it's...
Sorry?
So it's the advantage of using the axiomatic semantics against the operational semantics?
It's the difference is not that we use axiomatic semantics. Even NeedHack in Power uses some sort of axiomatic semantics. The difference is that instead of enumerating interleavings, we're just enumerating all the execution graphs a program may have. I don't know if this answers your question, but...